Once again, good evening everyone. Thank you for coming. And today is the continuation of our previous lecture where we have been discussing what was basically going on with AI for the couple dozens of years and what is it that's probably coming to us at certain dozen years as well. We have been discussing the superintelligence. We have been figuring out how far we are from that superintelligence, whether we should fear or should fear not of those artificial intelligence algorithms. So right now I would like to continue from where we started. We had this little discussion when we were trying to figure out all the possibilities. So today we're going to talk about, as you can see, statistics on steroids. Basically I used this term on our previous conversation, and what I mean by that is that generally what we tend to call artificial intelligent algorithms as of now are just statistical methods, which are well known, but they are highly boosted and powered by computational power of machines that we have right now. So what do we know about super intelligence or just artificial intelligence or general artificial intelligence? We know that machine can forecast, it can memorize, reproduce, or choose best item in whatever you have, like the labeled data. Now, we have learned that machines actually cannot create something new, and we have been talking that basically whatever new machines can produce, it produces it from some sort of a background. Then machines can get smart really fast. It's also somewhat of not happening right now. Go beyond their task. So apparently we can achieve very high, admirable results only in cases where the machine operates within the specific task. And finally, we have learned that machines cannot kill all humans, which are kind of a good news for us right now. So, in order to figure out why that happens and what are those limitations, we need to figure out how we kind of operate. So we know that humans learn from past experiences, while machines basically follow instructions. That is like the principal thing that differs us in how we operate. In a way, you might say that machines also learn from experience, but that is actually the next step. And if we think about it really hard, whenever we kind of produce those experiences or those data sets that we incorporate to our algorithms, they are generally have the exact instructions on how to operate with them. Now we need to figure out how exactly artificial intelligence programs works and how it focuses on which cognitive skills it focuses on. So when we talk about AI programming, we talk about learning, reasoning, and self-correction. Okay, anybody here wants to tell us what it means to actually learn for the machine? Any ideas? Okay, not yet warmed up, I'll help you a little bit. So learning in terms of machines means that machine collects a lot of data from various sources, and there is a task to kind of systematize this data and then finally produce some sort of an algorithm based upon the data that it has collected. Now, what is then reasoning in terms of algorithms and how machines operate? Any ideas? Okay, still not warmed up. So reasoning means you might have multiple various algorithms in which machine can approach the particular problem-solving situation and scenario, and machine actually possesses some sort of a mechanism that helps it to figure out which algorithm will be more appropriate to the certain task and the certain problem. And finally, self-correction, I mean, it's pretty self-explanatory on its own. It means that the algorithm in which machine operates kind of always gets back to a certain point when it receives data, processes in a certain way, and then gets back to receive more data and get more additional information. We'll talk about it a little bit later. So now, what do we know about different types of artificial intelligence? So obviously there are like tons of different methods, and I didn't want to go through all of them and exactly how they work, so I just need to give you a general understanding of what is there right now and how it works. So we have so-called reactive machines. It's like the very basic thing. What does it mean to have a reactive machine? Reactive machine can perform simple classification and pattern recognition, obviously. I mean, I don't know if it requires any additional explanation, but basically, you know that machine can work with data, can collect it and somehow systematize. Well, when we talk about systematic approach to data, it's all about classification and pattern recognition. So we can find correlations in data and find some certain results in it. All parameters are known, obviously. So reactive machines, as it states from the name, can react. That means that they need to really understand the environment and all the parameters of how they operate in which conditions. If the conditions are uncertain, reactive machines are not able to perform any tasks. And finally, they are obviously better than humans due to the faster computational capabilities of the machines. That's what we actually had a talk yesterday, and this is one of the things kind of that doubted everybody, like, is it even possible that if we have a huge computational power to kind of grow the consciousness? Well, here we go to the other category of artificial intelligence, which is called limited memory. It can work with complex classification tasks. It can make predictions based on historical data. This is a crucial part, actually, because reactive machines cannot actually process any historical data. So it can gather data in the situation, in the moment, and kind of try to figure out some correlations and produce reactions. Obviously, the limited memory machines, they can make predictions if they can go back to history, if they can analyze the situation, they can find the correlation, not in the moment, not in the reactive state, rather in state when they can analyze various scenarios. And basically this is the current state of artificial intelligence, which we have right now, because the theory of mind is somewhat considered to be the next step when the machine would be able to understand human motives. Right now we don't have quite that algorithm yet, so how can we perform it? Then it can deliver personal experience, or would be able to deliver personal experience. Now, it is also kind of a hard task to crack, because what it means actually, personal experience, when you work in the paradigm of instructions, right? So like a very strict thing with instructions. Finally, it can learn with a lot fewer examples. And this is actually a thing that now kind of a possibility, and we'll talk about it later, like there are algorithms that are already breaching this particular problem. And finally, what we kind of expect when we develop the technology of artificial intelligence is self-awareness, or actually human-level intelligence. Basically, the idea of self-awareness is the capacity of machine to bypass human intelligence. So when it is self-aware and it is having this possession of computational power and all the capacities that we have been discussing previously, it will be able to surpass human intelligence by far. So now, we obviously come to the state of current AI. We traditionally talk about machine learning. I mean, is there anybody here in this room who have never heard about machine learning? Raise your hand. Okay, there's no shame if it is so. But yeah, I'm pretty sure about that, because it is a very hyped terminology. I mean, there are a lot of articles, and we'll talk about it later as well. But generally, what is machine learning? And this diagram here kind of shows how it emerged. So basically, machine learning works with data, it works with algorithms, and it traditionally has something to do with features. And while with features, well, we should figure it out right now. This is one of the models that kind of resembles the general idea of machine learning. So we have some sort of a labeled data, and by labeled data, I mean some sort of a data set about some, I don't know, situation, whatever. We'll have an example a little later. When labeled, it means that kind of a machine knows with what it is dealing, actually. So we have some sort of an algorithm that kind of describes how this data would be handled. Now, there is also the supervisor who are traditionally helping the algorithm to figure out some stuff. A supervisor who is human, who actually can understand various types of data. So it can, on one hand, provide a training data set or describe the desired output. Now then we process this algorithm and data, and we kind of create the output, which helps us basically figure out what we're looking for. Well, to better explain, let's say we have here, I don't know, Max, and he likes music, and he can like or dislike various songs. Now, can you provide me a couple of examples? What do you think might be the features based upon which Max likes or dislikes music? Any ideas? Anybody? Like, what do you think can be there? Like you,
Genre.
okay, genre. Okay, good one. Anything else?
Like pace, fast pace.
Fast-paced or slow-paced music, great tempo. Another one?
Lyrics.
Lyrics. Okay, yeah.
Who sings the lyrics, female or male?
Okay, great. Well, actually, you got all of them. So we have tempo, we have genre, we have intensity, and we have gender of voice. These are the 4 features that I have provided for this particular situation. So apparently, we can predict what type of music Max likes based upon these features. Now, how does it work? Let's say we have this little chart here, where on one side we have tempo, and then we have intensity. So he's probably listening multiple tracks, and he checks what he likes and dislikes. Let's say he listens a lot to tracks with a fast tempo and with soaring intensity, and he likes these songs. On the other hand, when he gets the songs that are more light and relaxing, he probably doesn't like them. I mean, these are just 2 features, and you can imagine that we can extrapolate it further with other features. It's just based on 2 particular features, and now you can add also the gender of voice, for instance, and it would be like a 3rd dimension, and it can go on and on. We kind of have this labeled data set. So he labeled it for us, he said like or dislike. Now, why do we need this information? Well, basically we can create kind of this predictions of where the songs that he might lie. So for instance, if we find this another new song labeled A, what do you think whether Max will like it or not?
He will like it.
He will like it, obviously, because it lies in the soaring intensity and fast tempo, what he likes. So this is an easy one. Now, what happens if we get a song B, which is somewhat in the middle, with the middle intensity and the middle tempo? What do you think? Will he like it or not?
Equal chance?
Equal chance. Mm-hmm. Well, machine learning cannot work with equal chance. It needs to kind of predict based upon the labeled data set. It needs to figure out, will he like the song or not? By the way, this is the very algorithms that are used in your apps where you listen to music, because you know the recommendations come pretty much that way. It asks what you like and then figures out various features like what you like. But what will happen if it's somewhere in the middle? Will it recommend you this song or not? And to be honest, it should be easy to see from here. Any other ideas? How can we understand it?
He'll set it to probably and then just rarely recommend something of that genre.
Rarely recommend something of this genre. Well, it's more about figuring out the statistics. As I mentioned, statistics on steroids. So we create another labeled area, and now if we kind of separate this particular sector, we'll see that the likelihood of him liking this song is actually 3 versus 1. This is how it makes decision. So the algorithm will make a decision or make assumption that Max will like this song. So this one will get into the recommendation because you can see there are more green circles in this data set than red ones. So apparently, probably, but then once again, if he dislikes it and it gets to the labeled data, then the data set changes. So it works pretty simple. The more data, the better the model, and the higher the accuracy. The more songs he will like, it will create a bigger data set. We can understand it a lot easier and predict what he likes and what he dislikes. Especially we have multi-dimensional model. Now, in terms of machine learning, there are, well, to be honest, there are a lot of versions of machine learning, but we'll talk precisely about 3 particular versions. So one is called supervised learning. Supervised learning is a pretty common model. Well, you can see that there is the classification model. This is the one that we have been seeing before. The regression model as well. On the other hand, we have unsupervised learning. What does that mean? Supervised learning is, you see the exact differences in supervised model. We have kind of label data. In unsupervised learning, we might use clustering. That means, as you can see, that when machine sees this kind of clusters of data, it can predict whether so basically it can label it itself. It has an unlabeled data. And there are various modes as well, like for instance dimension reduction. It's just another way to express this clustering. And another one is reinforced learning. Now we shall talk about each of them on quick examples to try to figure out how they actually work. So let's see. Supervised learning. Let's say you have a couple of coins and you know exactly what are their weight. Well, in that case, what do you think would be the features and what would be the labels? Well, we have been talking about labeled data, and label is kind of a, like with Max and his songs. Yeah, he likes it, dislikes it. Yeah, exactly. Thank you. The weight will be the feature and the currency is the label. So it is kind of easy at that. Why do we need that? Because when we show a certain coin to our machine learning algorithm, it will try to figure out how much does it weigh, so we can make the assumption of what type of currency that is. And basically this is a supervised learning. We have provided a supervised solution to our machine showing like what is the weight and how it correlates with the currency. A pretty easy one. Now, once again, in terms of supervised and unsupervised, you can see that the pretty much difference is that in terms of unsupervised machine learning, we do not have the label data. So let's say you have just hundreds of different coins, each with every weight, and kind of you actually have no idea, no clue what is that currency. But maybe when you have a lot of them, maybe you can, using some various features, actually figure that out without knowing that. Because in terms of supervised, you can see it is kind of a different story. So basically, when we talk about clustering in supervised learning, there is such an algorithm as, say, similarity-based clustering. That means that when you kind of have similar but kind of little deviations of information in your data set, you can possibly predict that it has something to do with that particular cluster. Or it might look like this, for instance. In algorithm of clustering, it will probably see something nice, like we have all the bumps. Now, going back, so why do we use it? We use it always, and I mean a lot of times we use it in marketing, and you know that kind of based upon the operations that you do on the internet, for instance, or if you buy something, then it probably can predict like what you want to buy next based on this type of algorithms, because we do not quite know what is it that you're going to do, so a machine kind of tries to predict what you're going to like based upon your operations. But it is not quite labeled, so yeah, this is how it works. Now, back to reinforced learning, and speaking of what it is and how this works, the reinforced learning is a completely different beast. Basically, reinforced learning means that if we show a picture of a dog to our computer, and we'll make some sort of an unsupervised assumption, like let's say it thinks that maybe this is a cat, and we need to say no, this is not a cat, so we kind of get back to the machine and say make another guess. So it looks to another dog, and apparently already it knows that it's most likely not a cat. It makes an assumption that this is dog, and we verify and we say yeah, this is a dog. So at this point, machine kind of starts to learn. And once again, the more actions it have, the more dogs it see, the better it will distinct dogs from cats. We helped it, we reinforce it. This is actually, and the example with animals is pretty much the way we train our animals. If animals sort of do something you don't like, you kind of well, you do some sort of actions to make animal feel that this is wrong. I know you either scream at it or just trying to explain it, whatever approach you see fit. The idea is that you train it, you reinforce their learning by the example, saying what's right and what's wrong. This is how the reinforced learning works. Now, I have here a couple of examples and I want to hear your ideas generally. What do you think? So, 3 examples. First one is you probably have seen it. You know, the Facebook face recognition. You turn on your phone and Facebook asks, like, do you know this person? Is it this particular person? And this is obviously a machine learning algorithm. Now, how does it work? What do you think it is? Now, the next example is Netflix movie recommendation. How does it recommend? What type of machine learning it is? And finally, we have the fraud detection. Some activity in the banks or the credit cards or something like this. And there are machine learning algorithms that actually also can take some assumptions to figure out whether it's fraud or not. Now, any ideas anybody would like to try? Which is what type of machine learning?
I guess the face recognition kind of deconstructs the face in order to make it into patterns that it can later identify, such as this is the eyes have this kind of spacing, and it does that based on projection of the face.
Yeah, well, what do you think in that case? Does that supervised learning, unsupervised learning, reinforced learning, what does it feel to you?
I think it's unsupervised learning. It just, you throw in a lot of pictures of people and faces, and it kind of draws some sort of connection between them, like the distance between the nose and the mouth, the gender and race sort of thing.
So you think it's unsupervised?
Yes.
Okay, any other ideas? So okay, once again, supervised learning is when we have the labeled data. We have the data that is somehow marked by the statistics. Then unsupervised learning is when we have kind of a similar groups that looks like the same. And reinforced learning is when the machine can make assumption and we fix it. So the actually Facebook recognition is kind of a tricky one, because I would say on one hand it is a supervised learning due to the fact that, I mean, it would have been unsupervised learning in case if it will kind of make assumptions on its own without asking us like whether it is this person or not. Now we can label this data, or it might even be considered a reinforced learning if we kind of keep saying that this is not this person. But it actually depends on how the algorithm is fine-tuned, so there are options in that sense. Now, when we talk about Netflix movie recommendation, how does it work? I mean, not in terms of machine learning, but generally. So you turn on your Netflix account or whatever you prefer, and you see, like, you probably would like this and that and that. How does it make this assumption?
Similarity-based learning, because the next recommendations are usually based on genres, actors and so on that we have watched earlier, and that might be unsupervised learning.
Yeah, that's true. That's true. Thank you. It is really indeed unsupervised learning, and the general idea is that kind of people like or dislike genres. They kind of leave some data, but based upon other people's like ratings and stuff like this, the algorithm receives various information and it's trying to kind of group it. And indeed, it is the kind of, I think it is a little bit both of it. It is at the same time the similarity-based learning, and it is a great example of an unsupervised learning. Now, speaking about fraud detection, what do you think about fraud detection? Like a suspicious activity, whether it's working or not. What do you think about that? Well, that's tricky because fraud activity is probably not labeled. I mean, if you are a banking person, you do not know how fraud will like, or I mean, once again, there are possible options depending on how you fine-tune this machine learning. But one of the options is that, let's say, the banking experts try to label various types of fraud, and so when the algorithms try to see like, okay, this is probably some fraud, it might react. But on the other hand, it might be even generated in a different way. So, for instance, it have kind of the groups of operations which are familiar to the machine, like the general transactions that it have, and then a certain data entry appears that seems to be a little off. So, for instance, you constantly making your, I don't know, transfer operations in one particular city, and boom, all of a sudden, in 4 a.m. it happens somewhere in Beijing. It's probably suspicious. So it will find this particular data point, and it will make it suspicious, so it will not use it until it is confirmed or not confirmed. And so we will train like, yeah, sure, I just, I don't know, pass my car to Beijing at 4 a.m. and it's fine, maybe, or something like that. So yeah, it requires additional checking. Now, okay, we had this little conversation with possibilities. Have you ever been using the system for automatic translation on Facebook? Raise your hand who has did it. Okay, not much of you, because the funny thing is that, well, actually, it works with the so-called LSTM, the long short-term memory systems, which are a lot like how we operate, and this is also the neural network that is designed specifically to kind of translate it really fast. And the thing is that it actually performs 4 billion times a day. This translation was on Facebook. 4 billion times a day, can you imagine? 4 billion times a day means that it actually translates 50,000 sentences per second. Another 50,000 sentences, and another 50,000 sentences, and so on and so on. So, how does it work? It is a little bit different technology. As I mentioned, it looks like our neurons, so it is a neural network. Now, the next step that we have right now in neural networks is the deep learning neural networks. As you can see, I mean, you will not discuss it kind of in very broad detail. The idea with deep learning neural networks is that they have more hidden layers that process the information. So now, one thing before we talk about deep learning is we need to actually understand what it is and how it differs from machine learning. Because when you read the press on the internet, there are a lot of stuff going on. As you can see on this little graph, I say that basically machine learning is the kind of a part of artificial intelligence, and there are many various algorithms for machine learning. Now, one of which is neural networks, and the deep learning is a particular version of neural networks. Why I show it to you this way? Because, I mean, you can read on the internet something like, will neural networks make machine learning obsolete or extinct or whatever? And I mean, it sounds to me probably like, will wheels change cars? So in order for you not to be fooled, this is basically the part of machine learning as well. And deep learning is a particular example. So now, how does it work? For instance, we have the classical algorithm for natural language processing, just like with translation. So it kind of receives additional information, and we have the algorithm with various instructions, which helps us pre-process this data, then model this data, and figure out the output, like the sentiment analysis, the classification, and so on and so forth. Now, when we apply the deep learning-based natural language processing, the idea is that we have various processed documents, which kind of goes for our hidden layers. We have various functions that analyze them and then figures it out later. So we do not need to kind of prepare all of this pre-processing and modeling. That's the cool idea of how deep learning works. It kind of simulates how your brain works to a certain extent, apparently. So the actual deep learning revolution started in 2012 when a bright team of engineers from Stanford created and designed this 9-layer neural network to work with images. It was called the ImageNet. And the idea was that they were running this like database of 10 million YouTube frames for 3 days and computed them on 16,000 CPUs. And well, you see, the thing is that it worked pretty well back in the day in 2012 because it had a very good recognition accuracy, especially trying to figure out cats, and which is probably not that strange when you think that the neural network was trained on the YouTube, right? So right now, at that point, specifically a little bit later to the future, to 2016, the machines got really better with the image recognition. And not even the image recognition, but also the playing Pac-Man, for instance. And the very same algorithm, by the way. And finally, in 2016, the DeepMind, the guys from DeepMind have created this Alphago Algorithm. The idea is that we already knew about algorithms who knew how to play chess. And I mean, it is supposed to be like you could use machine learning and deep learning both to make machine play chess. But now playing Go is a completely different thing because it is considered to be a very sophisticated and tricky game of strategy and so on. And in 2016, they launched this AlphaGo, and it kind of produced very interesting results. Well, you see, first in 2016, they created this AlphaGo which could play Go, and it became the first actually program that could master the neural that could beat the master. But it had a couple of knowledge. It had the human data, the domain knowledge, and it knew the rules of the game. It was not enough, and already in 2017 they have created the AlphaGo Zero, which kind of learned to play on its own. So basically it didn't have any human intervention and domain knowledge, but it only knew the rules. Well, basically how it works, the thing kind of played with itself for a lot of multiple times, and we'll get a bit later, and finally produced the result where it could play against humans and actually win against the masters of the game. So finally in 2018 they have developed the Alpha Zero. The idea was that it could use the same algorithm for 3 different games: Go, chess, and shogi. The exact idea is that the same algorithm could be applied for all 3 games. Was kind of astounding back in the day. And then in 2020 they have designed Mu-Zero. This is the algorithm who could play not only with the same algorithm in 3 games, but it also didn't use any knowledge of the rules. Moreover, it could apply the very same algorithm to video games like Atari games. What does that actually mean? The general idea behind it is that if the algorithm doesn't know the rules, then it will have to explore the environment. It will have to figure out the rules on its own. It will have to know how to play by trying to do something and figure out the rules on its own. Then it could apply the same logic to different games, but playing chess is one thing. It is a very kind of a deterministic environment. Now what about playing Pac-Man or playing some other games? And I mean, they have used this very algorithm to play StarCraft and Dota. And the general idea was that it kind of learned the strategy the more it go. It figured out the rules and the boundaries and the limitations, and figured out on its own the best strategies. So before Mu-Zero we had Alpha Zero that played only the board games like chess, shogi, and Go. And you see here we have statistics on how it actually managed to win or lose. And well, you see the results are pretty impressive. So the green ones are the times that AlphaGo has won. And basically, Alpha Zero at that point. And basically what it has done, it kind of produced a situation where it could play with other algorithms and beat them as well. Well, we need to keep in mind one particular thing. You see, the deep learning is an interesting method, and we will also go into a deeper discussion of how it works and what are the possibilities of deep learning later. But generally, deep learning works well when we have tons of data. Processed or not processed, doesn't quite matter. The idea is that when we have tons of data, it works well, and it performs a lot better when it works with kind of industry giants, right? Like for instance, like Google or Apple, basically the people who can receive, or Facebook, who can receive tons of data. And then it actually shows a very good performance. otherwise, like it beats the older algorithms, because older algorithms, they at certain point when the amount of data keeps on growing, it kind of stops there. So yeah, this is kind of the general idea. Well, at this point, I would like to have a quick stop, and I think at this point we need to discuss what we have heard and ask the questions. And I seen your hand. I think there was a question. Can you please pass the microphone? Who is the final possessor of the microphone? Thank you.
Thank you, Aleksey. One question on this game, for instance, AlphaZero. Was it trained at all in the beginning by some supervisor who was explaining it, for instance, chess and these other games? Or was there never ever in its lifetime any form of training by a human?
Yeah, thank you for the question. This is a great question. The general idea of AlphaZero and why it was such a big deal, and even AlphaGo Zero, because it didn't have any supervised learning. So basically it knew only the rules, and it had the ability to play with itself. So on one hand, it kind of had the experience, but a personal experience. So it started to play with itself and try to figure out, I mean, you know the rules and you play with yourself and you kind of gain statistics, but you do not have any supervisor like we had before, like human data or domain knowledge. And while on one hand it is kind of pretty cool because it's on one hand the same statistics, but then the system needs to figure out, crack the code itself, like figure out whether it's doing right. And the coolest part with MuZero is that it didn't even know the rules. It had to figure it out on the go to kind of find the limitations while playing the different games.
Without any form of some human saying, yeah, this was good, this game you won.
Yeah, without any supervision.
So it was not, but how then can it know what is a win?
Well, it kind of plays, for instance, when it plays with other people or humans, like, I don't know, say, video games. I mean, the general idea was that they have applied the same algorithm in different games, and it kind of started to learn the environment. I mean, I probably lack myself a little bit of understanding of the core fundamentals that they break there, because, I mean, it is astounding to me as well. But like the general notion, what they promote is the fact that it is possible to deep learning while having various hidden layers of this neural network to kind of figure out on its own. I guess just like, I don't know, just like we might do at a certain point, to play with itself in various situations, then to go and play with other players and kind of without any reinforced learning from a human intervention.
Yeah, in a way, you know, if the machine is told, okay, now the game is over, people stop, then at least it knows that, okay, either me or the others won. But I suspect that still, you know, in the beginning they have to say, okay, you won or the others won. Or probably it will assume from the beginning, okay, I lost here. Something like this. Right?
Well, yeah, your question does make sense, and unfortunately I'm not very capable of that, because to me, I mean, the papers that I read on it, and they actually produced a paper on Nature in December 2020, and the way I saw it, it also amused me, because how I can actually say, it seems like only logical that at least a certain intervention should be done, like where you should stop or where you should start and something like that. But yeah, I think for me personally, it requires additional, you know, kind of learning. But right now, this is kind of a state-of-the-art algorithm that is fascinating. And while we were talking before about like how the algorithm might actually figure out stuff on its own, this is kind of the first step in the right direction.
So that MuZero is a deep neural network, right?
Yeah.
So when it, for example, plays chess, it learns the rules.
Yeah.
And then, do we have that very same algorithm that already can play chess when we let it play another game? Or is that just the same structure?
It's actually a good one. As far as I understood, when I analyzed this final thing, as far as I got it, it kind of uses the combined experience. So it's not like this algorithm can play various games. It's just that this algorithm can play all of them. So it kind of learns one thing, then goes to the other, then it probably goes back to that one. confirming what it knows. And the general idea and the interesting thing that they have tried out with the video games is that experience that they have brought from the board games like chess and Go, they kind of have incorporated there. So while not only exploring the rules and learning how to know, it kind of also learned the strategies. And the fascinating part is that when it had already developed on its own various strategies for chess and Go, it could have incorporated the same strategies or evolved versions of the strategies to the games like StarCraft. And that is what is interesting to that point.
How many hidden layers it has, mu0, and how many neurons per layer about?
Well, unfortunately, I do not know that information. They in the paper they only showed like a couple of the mechanisms on their own, but I'm not sure about the exact number, to be honest.
Do you have an estimation between so much and so much?
Yeah, well, no, I probably wouldn't be able to tell. I think I just added here as an example of like where it is going, but I haven't explored it to the extension like how many exact layers do they use. And I think that probably it's not only about the layers, but rather also about the specific algorithms that are there within the layers as well. No, unfortunately, I wouldn't be able to estimate. Okay. So, no more questions?
So mu0 was not given the rules, you said?
Yeah,
right?
yeah, exactly. And this is what is kind of amazing. This is why it actually really feels like the next step, because as we know of right now, and as we go to the very back of my presentation, the first thing that I have stated was that the kind of a theory of mind, which is considered to be not yet there, can learn from fewer examples. And as of now, if we not talk about mu0 or any other developments of deep mind, we kind of know that machine learning works pretty well when we have huge amounts of data, when we can make prediction on its historical data, and obviously when we talk about like big data analytics, it also draws from there. So kind of we can, yesterday when we were in a discussion, in the phase of discussion, we had this thing when like, at what point and how does it differ? Like a person cannot process that huge amounts of data, like for instance, like hundreds of pictures of faces of people or something else. I not quite remember what was the example. And so the machine learning can do it, and can do it pretty well, and can do it a lot faster than us. But still, in order to work properly, and as we talked before, the more data we have, the better the model would be, and so the better the accuracy will be. And finally, how should we create the machine that can achieve the very same results, but with a lot fewer examples, or even without any examples? So this is the step towards the theory of mind. It means that when we kind of keep developing this particular thing, this type of algorithm, and we can extrapolate it outside of things like chess, for instance, then it means that at a certain point this algorithm would be able to understand human motives and deliver personal experience. Just the way it originated, I mean, the very before, like in 2012 and even earlier, since I think since inception of the very first algorithm that were considered to be artificial intelligence, in a way, people try to apply it to various games, such as chess. And each time it was producing the better and better results. So yeah, Alphago was like the pinnacle at a certain point in 2012. But still, it worked on the bias of limited memory. Now when it can turn to the theory of mind, so first we do chess, and it is very kind of a control environment. Then we do other developments that help us go beyond chess and help us kind of transfer it to other things like predictions and so on. Like for instance, when you work with finance or when you work with different forecasts, whatever. I mean, the applications are almost unlimited. But the general idea is that if we can make this next step to the theory of mind, then we can talk about experiences and motives and understanding. And that means that we will be only one step closer to the human level intelligence, which is yet to be determined what it is and how it can be delivered. But just think about it, only one step before the human level intelligence.
That would be an interesting topic for the discussion on Thursday.
Yeah, definitely.
We should listen very carefully now to see where AI is.
I mean, at least I hope that this kind of a, approach will give a little bit more of understanding. And I mean, there are actually tons of versions of machine learning and, I don't know, like convolutional neural networks and stuff like this, but I didn't want to go to bother you really with that much details, because if you are really interested in how it works, for instance, like how machine vision works, then, I mean, there are tons of information. I didn't want to waste time here, just to give you some examples, like what has happened with particularly ImageNet, for instance, how good it became since its inception in 2012 up to the 2015, when it achieved almost astounding results. And now, 5 years later, we have kind of the next step of the theory of mind. So you can kind of get the progression that we are in, the track that we are on. So basically, before AlphaGo, we didn't have that much of that much of a breakthrough. So yeah, deep learning was already kind of evolving, but in 2012, it kind of was a solid step in the right direction. And I think this December 2020 is also a solid step towards another direction. Let's see, I mean, they are producing new results like every year. Let's wait for another December and see what's gonna happen in December 2021. Maybe they will play something else incredible. Yeah, so that's why we kind of need to understand the fundamentals, not necessarily the intricate details of working of each particular network, but rather how it operates. And our next step in our next discussion, the next lecture, will be more of like, since at the very first lecture we have been talking about like superintelligence, and we were at that point, now we're going kind of back on track when we see what is the current state of artificial intelligence, or at least what people tend to consider to be artificial intelligence, like the neural networks, machine learning, and deep learning. You can see yourself that it is statistics on steroid, basically. And I mean, we couldn't probably be able to talk about like cognition in the things like clusterization, right? When you see behind the curtain and know how it works. But then deep learning is somewhere already closer to how we can treat it, because it kind of assimilates the nature thing, kind of assimilates the way we think. That's why it is a little harder, and that's why it is called hidden layers, because you don't kind of design this network, but then since the design, it can, you know, go with a very unpredictable results. And it's not, you know, just a linear algorithm. It is a very sophisticated and intricate one. And so then we're gonna need to talk about how it correlates with nature later. What we're gonna be talking about, like what is then consciousness in terms of artificial intelligence. So what can we actually call it? If we kind of see that the modern examples are basically the best versions of math and statistics, and I think that would be like a better, I don't know, finalization of this topic. Okay, do you have any other questions, since we have a little more time? Okay, if there are no questions, I think that we can stop on this very point. Thank you for your attention. I'll see you in the next lecture.